The situation described presents a potential problem because the third section of the switchboard is rated at 1000 amps, while the incoming service and other sections are rated at 1600 amps. The National Electrical Code, or NEC, addresses overcurrent protection and feeder requirements which are relevant here. NEC Section 384.16 A. Overcurrent protection states that overcurrent protection shall be provided for each feeder conductor and branch circuit conductor in accordance with the requirements of this section. This means that each section of the switchboard needs to have adequate overcurrent protection to handle the potential current flow. NEC Section 384.16 B. Feeder overcurrent protection states conductors shall be protected in accordance with the requirements of 240.4 and 215.2 as applicable. This section directs us to other parts of the code that specify how conductors should be protected from overcurrents. NEC Section 240.4 A. General states that every feeder shall be protected against overcurrent by a circuit breaker or fuse. This is a fundamental requirement for electrical safety. NEC Section 240.4 B. Location of overcurrent devices states the overcurrent device shall be located at the point where the conductor receives its supply. This ensures that the overcurrent protection is effective in preventing damage to the conductors. Therefore, the 1000 amp section is undersized for the potential current it could be subjected to from the 1600 amp service. If the 1000 amp section is fed directly from the 1600 amp bus, then an overcurrent situation in the loads connected to the 1000 amp section may not trip the main 1600 amp breaker quickly enough to protect the 1000 amp rated components. Ideally, each section should be rated to handle the maximum current that could potentially flow through it, or have appropriate overcurrent protection to limit the current to the section's rating. Let's break down why having a 1000 amp section supplied by a 1600 amp service poses a problem. Firstly, overload risk. The 1000 amp section is designed to safely handle a maximum of 1000 amps of current. If the loads connected to the section draw more than 1000 amps, it creates an overload situation. Without adequate overcurrent protection sized appropriately for the 1000 amp section, the components in that section, such as busbars, wiring, and connections, could overheat and potentially fail, leading to a fire hazard. Secondly, inadequate overcurrent protection. While the main 1600 amp breaker protects the entire switchboard from overcurrents exceeding 1600 amps, it may not provide sufficient protection for the 1000 amp section. The 1600 amp breaker is designed to trip at or above 1600 amps, which is far beyond the safe operating limit of the 1000 amp section. Therefore, a smaller overload in the 1000 amp section might not be enough to trip the 1600 amp breaker, allowing the 1000 amp section to be damaged before the breaker eventually trips. Thirdly, code compliance. The NEC requires that electrical equipment be properly rated for the intended application and protected against overcurrents. Having a 1000 amp section supplied by a 1600 amp service without adequate overcurrent protection for the 1000 amp section violates these code requirements. This could result in failed inspections, fines, and potential liability in case of an electrical incident. Fourthly, coordination issues. Electrical systems are designed with coordination in mind, where overcurrent devices closer to the load trip before upstream devices. This minimizes the impact of a fault and allows the rest of the system to continue operating. In this case, the 1600 amp main breaker might trip before a smaller breaker in the 1000 amp section, causing unnecessary disruption to other parts of the electrical system. To correct this situation, one should firstly upgrade the 1000 amp section. The most straightforward solution is to replace the 1000 amp section with a 1600 amp section. This ensures that all sections of the switchboard are rated for the full capacity of the 1600 amp service. Secondly, add overcurrent protection. If upgrading the section is not feasible, install a 1000 amp circuit breaker or fuse at the point where the 1000 amp section is fed from the 1600 amp bus. This will provide overcurrent protection specifically for the 1000 amp section, limiting the current to its rated capacity. Thirdly, review load calculations. Conduct a thorough load calculation to determine the actual current demand on the 1000 amp section. This will help determine if the 1000 amp section is truly adequate for the connected loads, or if an upgrade is necessary. Fourthly, ensure proper coordination. Coordinate the overcurrent devices to ensure that the breaker or fuse protecting the 1000 amp section trips before the main 1600 amp breaker in case of an overload or fault within the 1000 amp section. Fifthly, consult with an electrical engineer. It is always a good idea to consult with a qualified electrical engineer to evaluate the specific situation and recommend the best solution. They can perform detailed calculations, review the existing electrical system, and ensure that all work is done in compliance with the NEC and local codes. Let's delve deeper into the technical aspects and considerations for this scenario. Firstly, understanding switchboard sections. In a multi-section switchboard, each section typically serves a specific purpose. The incoming section, often called the main section or pull section, receives power from the utility or a generator. Feeder sections then distribute power to various loads or downstream panels. The rating of each section should be based on the expected load and the overall system design. Secondly, analyzing the 1600 amp service. A 1600 amp service implies that the electrical system is designed to handle a substantial amount of power. The service conductors, main breaker, and busbars must all be rated for 1600 amps. If the downstream sections are not adequately rated, it creates a bottleneck and a potential safety hazard. Thirdly, detailed look at NEC requirements. The NEC provides specific guidelines for sizing conductors, overcurrent protection, and equipment ratings. Article 220 covers load calculations, which are essential for determining the appropriate size of electrical equipment. Article 240 addresses overcurrent protection, including the selection and placement of circuit breakers and fuses. Article 384, which has been replaced by Article 408, provides requirements for switchboards and panel boards. Fourthly, importance of overcurrent protection. Overcurrent protection devices such as circuit breakers and fuses are designed to protect electrical equipment and conductors from damage caused by overloads and short circuits. These devices interrupt the flow of current when it exceeds a predetermined level, preventing overheating, insulation breakdown, and potential fires. Fifthly, calculating load and demand factors. Load calculations involve determining the total current demand on each section of the switchboard. Demand factors are used to account for the fact that not all loads operate simultaneously at their maximum rating. These factors are applied to a calculated load to determine the minimum required ampacity for the conductors and equipment. Sixthly, coordinating overcurrent devices. Coordination studies are performed to ensure that overcurrent devices trip in a selective manner. The goal is to isolate a fault to the smallest possible area, minimizing disruption to the rest of the electrical system. This involves selecting breakers and fuses with appropriate time current characteristics and adjusting their settings to achieve proper coordination. Seventhly, addressing harmonic currents. In modern electrical systems, harmonic currents can be a significant concern. Harmonic currents are non-sinusoidal currents that can cause overheating of conductors, transformers, and other equipment. If the load connected to the 1000 amp section generates significant harmonic currents, it may be necessary to derate the equipment or install harmonic filters. Eighthly, considering future expansion. When designing an electrical system, it is important to consider future expansion. If there is a possibility that the load on the 1000 amp section will increase in the future, it may be prudent to install a larger section now to avoid costly upgrades later. Ninthly, physical inspection and testing. A thorough physical inspection of the switchboard is essential to identify any potential problems, such as damaged components, loose connections, or signs of overheating. Testing, such as insulation resistance testing and contact resistance testing, can help to verify the condition of the equipment and identify potential weaknesses. Tenthly, documentation and labeling. Proper documentation and labeling are crucial for the safe and efficient operation of the electrical system. The switchboard should be clearly labeled with the voltage, ampacity, and other relevant information. Updated drawings and diagrams should be readily available to maintenance personnel. In summary, the situation with the 1000 amp section in a 1600 amp service is a problem that needs to be addressed. The NEC requires that electrical equipment be properly rated and protected against overcurrents. Ignoring this issue could lead to equipment damage, fire hazards, and code violations. It is crucial to take appropriate action to correct this situation, such as upgrading the section or adding overcurrent protection, and to consult with a qualified electrical engineer to ensure that the work is done safely and in compliance with the NEC. Addressing this discrepancy is not just about meeting code requirements, but also about ensuring the long-term safety and reliability of the electrical system. A properly designed and installed electrical system will provide years of trouble-free operation and minimize the risk of electrical incidents. Furthermore, regular maintenance and inspection are essential for maintaining the integrity of the electrical system and identifying potential problems before they become serious. This includes periodic testing of overcurrent devices, tightening of connections, and cleaning of equipment. By following these best practices, you can ensure that your electrical system operates safely and efficiently for many years to come.